Hey everyone, today we're going to tear down something that, let's be honest, powers just about everything in our lives: the electric machine. They seem so complex, right? But what if I told you the entire world of motors and generators is built on one single, incredibly simple idea? Let's go find that secret.
I mean, really think about that. Not a dozen different rules, not a bunch of complicated physics, but one single force. A force that we've learned to shape and control in countless ways to create motion. It sounds like something out of a movie, but it's the reality humming away inside your car, your drone, even your blender. So, what is this foundational secret? Well, we're about to crack open what you could call the genetic code of all electric motion. This is the one rule to rule them all.
And here it is. It's called the Lorentz force, and it's shockingly simple. You take a wire, you run some electric current through it, and you put it in a magnetic field. That's it. The wire gets pushed. You have current, you have magnetism, and boom, you get motion. This one little push is the fundamental building block for every single electric machine ever made.
Okay, so a single push is cool, but that's not going to power a Tesla or get a fan spinning, right? The next piece of the puzzle, and this is where the real genius comes in, is figuring out how to turn that one-time nudge into a smooth, continuous spin. The trick is all in the shape. Instead of a boring straight wire, you bend it into a loop. Now, think about it. The current flows up one side and down the other. So the magnetic field pushes one side up and the other side down. And just like that, you've created a turning force, what engineers call torque. We've gone from a simple push to a powerful twist. But wait, there's a problem, a big one. Once that loop flips past standing straight up, the forces would actually flip too, trying to push it back where it came from. It would just sort of wobble back and forth. It would never make a full circle. So how do you fix that? The solution is this beautiful little device called a commutator. It's basically a really smart mechanical switch. Right at that perfect moment when the torque is about to reverse, this little split ring thing cleverly reverses the direction of the current going into the loop. By flipping the current, the force keeps pushing in the same direction over and over. And voila, you have smooth, continuous rotation. So simple and so brilliant. All right, so now we have the basics, right? We have the force, we have the twisting torque, and we have the secret to a continuous spin. This is the point where the floodgates open, and we see this incredible family tree of motors start to branch out into a wild diversity of machines. You know, believe it or not, every single electric motor you've ever laid eyes on fits into one of these three big families. You've got your AC machines, your DC machines, which often use those physical commutators we just saw, and then the modern marvels, electronically controlled motors, which let computers do all the clever switching. But here's the thing. Despite all the different types and names, every design choice really just boils down to one question. How are we going to create and control the magnetic fields to play with the electric currents? That's it. That's the entire game. For instance, check this out. It's a fundamental choice an engineer makes. Do you want to use these salient or, pointy poles that stick out to really concentrate the magnetic field? Or do you go with a non-salient, totally smooth cylindrical shape? Just that one decision about the physical shape completely changes how the motor performs. And here's another one. Where do you put the copper wires? Do you tuck them safely into these iron slots to protect them, which makes the motor super tough? Or do you put them right in the air gap between the spinning and stationary parts? That slotless design gives you this incredibly smooth control at low speeds, but it's more delicate. It's always a game of trade-offs. Now this was a huge leap, a real game changer. The classic motor had the windings on the spinning part, the rotor. But some clever engineer asked, what if we flipped it inside out? Let's put the heavy windings on the stationary part, the stator, and put the lightweight magnets on the part that spins. Suddenly, you didn't need the brushes or the mechanical commutator at all. And that's how we got the super reliable, super efficient, brushless motors that are absolutely everywhere today. Okay, let's zoom in on the undisputed champion, the workhorse of the entire industrial world, the AC induction motor. Now, to really understand how this thing works its magic with zero brushes and zero permanent magnets, you need a really good analogy. So let's start with a simple transformer. You apply an alternating current to one coil of wire. That creates a constantly changing magnetic field. This field then magically induces a current in another coil sitting nearby. It's like transferring power through thin air. No wires touching. Now, here's the brilliant part. Imagine you could just crack that transformer open and let that second coil spin freely.
Well, that's exactly what an induction motor is. The stationary part, the stator, is your first coil. The spinning part, the rotor, is your second coil. The magnetic field from the stator induces a current in the rotor. And that current, now sitting in a magnetic field, well, it creates that same Lorentz force we started with. It's literally a transformer that's free to spin. In the design of that spinning coil, it's just genius. It's not made of delicate wires. It's this super rugged cage of solid metal bars all connected at the ends. They call it a squirrel cage rotor. There's nothing to wear out. No brushes, no magnets, nothing. It's the reason these motors can just run for decades without anyone ever touching them. We are so close to the end here, but there is one last beautiful, elegant truth we have to talk about. The physics here, it's not a one-way street. It turns out that every single motor is also, deep down, a generator. They are two sides of the exact same coin. Remember that first rule we learned? Current in a magnetic field creates a force. Well, the universe loves symmetry, so the reverse is also true. If you force a wire to move through a magnetic field, you create a current. That's how a generator works, and it's the exact principle behind regenerative braking in an electric car. When you hit the brakes, your motor literally becomes a generator, turning your car's motion back into electricity to charge the battery. So this amazing duality means that any electric machine can really operate in 4 different ways. It can be a motor, speeding things up forwards or backwards, or it can be a generator, slowing things down, braking, while they're moving forwards or backwards. Motoring or generating, clockwise or counterclockwise, it's all the same hardware. And this quote just sums it all up perfectly. Every single one of the thousands of motor designs out there isn't some totally new invention. It's just a unique, clever engineering solution to the same puzzle. How do we manipulate magnetism and electricity to get the job done better? So let's just recap. We started with one single, simple law of physics, the Lorentz force. From that one little push, engineers figured out how to make a loop, create torque, get it spinning continuously, and then they just ran with it, creating this staggering family of machines, all by making smart choices about shapes and materials. It's incredible. From one law, infinite motion. And that brings us to the end. So I'll just leave you with this question. The next time you hear that quiet hum of an EV pulling away or see a drone just hanging in the air, are you going to see a mysterious black box? Or are you going to recognize a distant cousin in this huge, brilliant, and incredibly ingenious family? Thanks for joining me.